Okay. So, we have established a relation between between the discrete type Fourier transform and analog Fourier transform, where there is an analog function given. Okay. There is an analog function given, you are sampling it and forming a sequence out of it. The DTFT of this sequence at a frequency small omega, digital frequency, is related to the analog Fourier transform of this parent sequence, parent function at an analog frequency capital omega, where capital omega and small omega are related like this. So, if you want to find the DTFT as small omega, you should substitute capital omega as small omega by t, that means radian per second, and the summation. Now, this looks a bit complicated, but we will analyze it and then some interpretations will follow. But before that, one small observation I feel tempted to share with you, that is we considered this function. This is called a Dirac comb, because as such it looks like a comb, but this is another beautiful property, that this is the ST. How do we obtain? It was a periodic function in time over a period t. So, we expanded in Fourier series, not transform, Fourier series of this form, nth harmonic n times fundamental frequency omega naught came, omega naught was 2 pi by the period t, corresponding coefficient on Cn, n from minus infinity to infinity. Cn was given by the formula, standard formula in Fourier series. We got Cn to be common, 1 by t for all n. So, substitute that, it comes out of the summation, this is what you have. This is the ST. Now, if I take the Fourier transform of this ST, then that means the right hand side also you have to take the Fourier transform. But you know, u to the power j, any frequency, actually if you take a DC function, its Fourier transform is 2 pi delta omega. Okay, it comes from the reciprocity. The delta in time domain gives rise to flat in frequency domain, flat in time domain gives rise to delta in frequency domain, but there is 2 pi comes, because in the inverse Fourier transform 1 by 2 pi comes before the integral, that creates this problem, 2 pi comes. So, if I have got a function, so I give it a name, say ut, not u stands for unit impulses, unit step function. So, let us give some name, say RT. Okay. Now, suppose I have got, if I multiply RT with some frequency e to the power j, some frequency, say some omega prime t, what will be the Fourier transform of this? It will be Fourier transform of RT shifted to the right by omega prime, right. But what is this function? RT is 1, so RT is 1 all throughout, okay, DC function. So, 1 into this is equivalent to this function itself. So, this function its Fourier transform is the original Fourier transform of RT 2 pi delta, but instead of omega it will be omega minus omega prime, it is shifted, right. So, if I apply this here, Fourier transform of the left hand side is same as Fourier transform of the right hand side, analog Fourier transform, and therefore, what is the analog Fourier transform? It will be 1 by t summation, every such component will have 2 pi delta capital omega and then shifted by this amount. Okay. Omega prime t, omega prime is n into omega naught. So, it is shifted by n into omega naught. So, 2 pi goes out, 2 pi by t, which is actually omega naught. Okay. So, you see this is again another Dirac comb in frequency domain also. Okay. At n equal to 0, it is delta omega. So, delta omega means it will have an impulse at 0 and not present anywhere. That at n equal to 1, it is delta. Of course, its height will be omega naught. I mean, its strength is omega naught. If you integrate, you will not get 1, you will get omega naught. Then at n equal to 1, delta omega minus omega naught, that means it will be shifted to omega naught, which is 2 pi by t, and its strength again will be omega naught. Then again next one at twice this side also, and dot 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 dot. So, you see in time domain it was a train of impulses separated by t, in frequency domain it is a train of impulses separated by omega naught, where omega naught is 2 pi by t, and here height was 1, they have the strength. So, if you integrate any impulse, you get area 1. Here if you integrate any impulse, you get omega naught. That is why it is called Dirac-Cope. It is a beautiful function. This train of impulses in time domain on Fourier transformation gives rise to again another train of impulses in frequency domain. Okay. This is just a side observation I thought of passing on to you. Now, again I come back to that relation we have derived, and we see its interpretations and all that. So, we will now consider an example. Okay. I rewrite that result here. The result which we derived was this, that if suppose x a t is sampled with period t, that is in a sample is x a n t, n times t, and that I call x n. X a t, it has got analog Fourier transform capital X a omega, capital omega. X n, it has got a discrete Fourier transform capital X raised by j omega. Then we have established that they are related like this. For any small omega of your choice, this is nothing but 1 by t summation capital X a, this analog j, you can put capital omega minus 2 pi by t. I am taking just j common, where this capital omega t is small omega, that is capital omega is small omega by t you can put. This is a relation. Okay. Now, what is the implication for that? Suppose as an example, we have a band limited function, say x a j omega. Again a word of caution, this analog Fourier transform also is a complex function of omega. So, I should, to plot it correctly, I should have one plot giving the magnitude versus omega, another phase versus omega. But just to explain my point of view, I really am not going into that description, I am just writing it x a j omega. Okay. But whatever logic I use here, that will be applicable if you draw the magnitude part separately and phase part separately. Okay. So, but there is a word of caution. Suppose it is goes up to omega h, h for highest, and this outside this is 0. Then I saw it is a band limited function, band limited up to some capital omega h. Okay. And now, suppose I am sampling it, this is a x a t, this is the thing. We are sampling it at a period capital T. Sampling frequencies omega naught, so long I said, so long I use the term omega naught. Now, I will call it omega s, s for sampling 2 pi by t. Same thing which I was so long calling to omega naught, I am just changing the name to omega s, where s is for sampling. So, this is sampling frequency, this is 2 pi by t, all right, 2 pi by t radian per second, omega s. So, this 2 pi by t I will call omega s, nothing else. In that case, what is the DTFT of that sequence? That is, after sampling I am getting a sequence, I have to find out the DTFT, this DTFT what is that? So, I have to use this formula, of which 1 by t is a scale factor. So, I am not bothered about this, I will only consider this. So, first I plot right hand side as a function of capital omega, then I have to finally plot it as a function of small omega, because I want the DTFT to be a function of small omega. But to start with, I plot the right hand side as a function of capital omega. That is why I always prefer to keep capital omega on the right hand side, small omega on the left hand side. First plot it in terms of capital omega, then change the words from capital omega to small omega. This way it becomes easier. Some books bring small omega here, so that left hand side is a function of small omega, right hand side also visibly clear, but that way I mean handling it becomes difficult. So, suppose I am plotting it. So, what will I get for n equal to, there will be n here, this n I missed out. So, n equal to 0, this is not present. So, it is only this original one. Okay. Now, suppose my analog frequency omega s, that is, this is nothing but this thing, this is nothing but n times omega s, 2 pi by t into n, 2 pi by t is omega s sampling frequency into n. So, n equal to 1 now I am considering. Earlier I took n equal to 0 out of this summation. So, capital X j omega, it was just original one. Now, I am taking n equal to 1. So, there will be 2 pi into 1 by t. So, this plot will be shifted to the right by 2 pi by t, 2 pi by t is omega s. So, instead of origin will be shifted here now. So, maybe it is like this. I choose this capital omega s to be sufficiently far, so that this does not overlap with this, but if omega is not sufficiently far to the right, they will overlap. For the time being, I am not considering that situation. Then n equal to minus 1 also you can take. So, it will be capital omega plus 2 pi by t, which means this will be shifted to the right, origin will move to minus omega s, so on and so forth. And then you multiply by scalar 1 by t, it does not change anything. Okay. So, this will be the summation function plotted here, dot 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 dot. Then you have to write this as a function of not capital omega, but as a function of small omega. So, wherever capital omega here is to be replaced by small omega by t. Capital omega is to be replaced by small omega by, okay. Or rather, wherever there is capital omega, you multiply capital omega by t, okay. It will amount to that much small omega. Okay. So, this is capital omega h, and likewise. So, it means at any capital omega, if it has so much of value, the same value, if I am plotting versus small omega, it will go to which small omega, that capital omega into capital T, radian per second into second. So, that much radian, second cancels, that much radian you find out, same value will move there. That is how one plot will be converted into another plot. All right. So, if this corresponds to small omega, here, the same this height, this same guy will move here. Okay. So, likewise, it might be likewise. Okay. Omega s. So, all points, if you have got omega h, at omega h this is 0, but omega h if it is 0, capital omega h if it is 0, what is the corresponding small omega? That capital omega h into t, radian per second into second cancels, you get radian. So, you can call it small omega h if it is capital omega h. So, this will be small omega h, which is capital omega h into t. At that point, this 0 will come. Okay. So, at every capital omega, whatever value you have, that will come to this plot at that capital omega times t, so much of digital frequency. This is how one plot will be converted to another one. Now, one very important thing here to see is this capital omega s, this value, this capital omega s will then move to what digital frequency? So, capital omega s into t, but capital omega s is 2 pi by t. So, 2 pi by t into t, t cancels 2 pi radian. So, this will always move to 2 pi radian, and it is independent of the sampling period t you have applied. Whatever be the period you apply, the sampling frequency, analog sampling frequency will always map to 2 pi. So, half of it, so this if it is omega s by 2, this will map to pi. Since this is to the right of omega capital omega h, pi is to the right of small omega h. Since this is to the left of this point, this is left of this point also here. Otherwise, shape will be same. Okay. By the same way, if it is capital omega s by 2, similarly minus capital omega s will map to minus 2 pi and minus omega s by 2, which I call half sampling frequency, that will map to minus pi. This is in between the two. So, this is also in between the two. This will be mapped like this. My diagram is not very good. So, this point is minus pi, this is minus 2 pi dot 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 dot. So, 2 pi, then there will be 4 pi, 6 pi, minus 4 pi, minus like that. Here the function was band limited. So, it is becoming 0 and after a while again it is starting and like that is periodic repetition. Okay. But there is no overlap between them. So, if I see the DTFT, it is a DTFT and DTFT is periodic. So, it is turning out to be periodic from minus pi to pi, whatever you have, that is repeated. So, if I just take out this function from minus pi to pi, suppose I throw away the right hand side and left hand side, just take out this becomes a replica of this function. Only from small omega you have to go to capital omega. There is a small omega, whatever is the value, you reflect it to small omega by t, that much capital omega the same value. So, you get back this, and of course, this 1 by t was used. So, you have to multiply by capital T now to cancel that, but you can get back. So, all information about original Fourier transform is retained here, its shape has not changed. We say aliasing has not taken place. There is interference from here to here inside, from here to here. If there are interference, there are overlap, the shape would have been lost. That interference or overlap is called aliasing. So, this is aliasing free. When can that happen? If this becomes 0, then we have got some place, then the next one starts. That is, if the half sampling frequency is to the right of this or at least equal to this, even if this starts from here, even if in the extreme case, if you have things like this, there is no gap, it starts directly here. So, this is your pi, half sampling frequency, this is minus pi, even then is fine. I will see from here to here, this part, I will not see right hand side, left hand side, this will be a replica of original Fourier transform, which means if this omega s by 2 is either to the right of, that is either greater than or at most equal to omega h. Omega s by 2, if it is greater than or equal to omega h, and at omega h this should become 0. So, if it becomes 0, it starts again. So, there is no overlap. If this happens, then we get a situation like this, or in the extreme case, if it is equal to, you get a situation like this where it starts from here. There is no gap left. This point matches, coincides with this and with this, therefore, you get things like this. But even then, this shape is the same as original shape. So, no loss of information. So, if this happens, then we can recover original Fourier transform from here, okay, and get back my original function. So, this condition should be satisfied. This is called Nyquist condition, Nyquist sampling rate condition or Nyquist theorem. It says that for perfect reconstruction, in order to be able to get back my analog function from the sequence, okay, because if I know the sequence, I know the DTFT, but from DTFT can I get back to the original analog Fourier transform, and therefore, by inverse analog Fourier transform on it, get the original time function x a t. For that, this kind of situation must prevail, that is, there must not be aliasing or overlap. This happens only this, which means omega s must be greater than or equal to twice omega h. That is, analog sampling frequency must be greater than or equal to twice the band limiting frequency. Firstly, it should be band limited, it must be 0 somewhere, that I call band limiting frequency, and then I should sample it at an analog sampling frequency omega s greater than or equal to twice omega h. Okay. This is called Nyquist sampling rate, or this is the Nyquist sampling theorem. All right. In frequency domain, in DTFT domain, it means pi should be greater than or equal to this omega h. okay, because pi comes from omega s by 2. Analog omega s by 2 maps to digital pi, because you multiply by capital T, omega s is 2 pi by T, replace all that, you get pi, you get pi here. Okay. This is the sampling theorem. On the other hand, if this is not satisfied, if suppose this is not satisfied, this is not satisfied, so what will happen is an alias thing. This is given as a function of capital omega first I am plotting. This is your this diagram I am drawing now, redrawing, but omega s is not that far, omega s is suppose here. So, it is around omega s, the same thing will come, around minus omega s, same thing will come, and after overlapping it will become like this, like that. So, if you see over this range, if you now plot it as a function of small omega, so you replace every omega by omega t equal to small omega, and you get a plot. You will have this up to here pi and minus pi, and then this continues. This is 2 pi, like this. But from here this is not this, so your information is lost. Okay. So, this is the essence of this Nyquist theorem. Now, this leads to a fundamental question, and there is a fundamental thing is DSP. Suppose there is an analog x a t is an analog band limited function. Okay. That is x a j omega like this. That is x a j omega. Actually, again I tell you, I am plotting a complex function versus omega, capital omega. Okay. So, for correct plotting, I should take the magnitude versus omega and phase versus omega. But again I repeat that whatever logic I am trying to build up, just for explaining that, plotting like that is okay. Technically it is not correct, mathematically it is not correct, but as far as conveying the information or explaining is concerned, you can get all that information from here only. Okay. That is, if you plot magnitude and phase separately, the same logic will hold good. All right. So, this is given to be 0 for omega, for mod omega greater than omega each. That is omega greater than omega each or less than minus omega each. And I am sampling it x a t sampled following Nyquist criterion, that is analog sampling rate omega s, which is 2 pi by t, t is the sampling period, that is say greater than equal to twice omega each. So, we have seen it does not lead to any aliasing. Okay. So, we have seen DTFT will be like this, replica of that will come here, it will be omega h and it will go up to pi and minus pi. This corresponds to omega s by 2, analog sampling frequency by 2, in digital domain maps to pi and minus of that maps here, and again dot 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 dot. Okay. Here also dot 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 dot. No aliasing. So, this shape retains the original shape, that is XAT, band limited, analog, sample following Nyquist rate. So, DTFT is like this. Okay. Question is, this DTFT is given in terms of samples, that is x n. If I know this. Okay. But from this DTFT, if I take out only functionally speaking, if I take out this much, nothing to, not to the right, nothing to the left. So, this function, then next small omega I replace by capital omega, and you remember DTF, to obtain DTFT from analog, we had multiplied by a factor 1 by capital T. So, 1 by capital T times this will be this. So, how would I go in the reverse direction, capital T times, okay. Then that will be giving me this function, and then I apply analog inverse analog Fourier transform on it, I get back XAT. So, this way XAT I can get back from Xn, and that is the famous formula, Nyquist interpolation formula, which I will consider in the next class.